answer those questions as we go if I keep concentrating. So this section is much more practical. It's about how you would move an application or as a user from a Cray XE6 to a Cray XE30, say like HECToR moving to Archer. So, continuity. There are many, many things which will remain the same, and it will be a familiar environment, hopefully, to all HECToR users. The big shock, there are relatively few big differences apart from the massively improved performance. All of the technology that I was talking about earlier ultimately is very much hidden in the background and should just lead to applications getting best performance. So Cray's vision for its supercomputers and its programming environment is that it should be also a high productivity as well as a high performance computer. So we continue to develop the Cray programming environment as a simple and consistent interface to users. And it's designed to allow users to scale to the largest processor counts they can and reduce the complexity required to do that. And this is a continued vision and between XE6 and XE30. So the default programming environment should provide you with the highest levels of application performance, a rich variety of the common tools that you already use and libraries, but also a consistent interface to these tools, libraries, and compilers, and hopefully do a lot of the automated work or routine work that other systems might not let you do. So we're committed to extending, developing, and refining the programming environment. For this, you need frequent communication with your users, so we get feedback from people working on site, like myself, or directly from users. So if you do have anything you think could be improved, then we're always interested in hearing, and we will do our best to sort of fit it to improve it. We also have strong links with our third-party developers, third-party vendors, really. People like RogueWave for TotalView or Alinea for DGT, or people providing some of the third-party software we use. So the ecosystem looks very similar to the XE6 ecosystem. We're still supporting a wide variety of software. Compilers, I think the change, we've introduced a stronger support for the Intel compiler, given the switch to Intel processors, and PGI, so the support is perhaps more limited. We're still supporting visual debuggers through Alinea and TotalView. We can do job management through the common Altair, Slurm, adaptive computing. I should leave that on, actually. So that was my email, but it wasn't an interesting question. And also, we've got full support for the standard set of tools that we distribute for performance analysis, so CrayPat, Apprentice, and Reveal, and also the standard set of libraries. The operating system remains the same. We're still going to be using Cray Linux environment. Default mode being the extreme scalable mode or scalability mode, ESM mode, which is basically about getting the maximum performance you can out of your supercomputer. It does require you to use the native communication libraries, the optimized MPI, but it's the best way of getting the best performance out of the nodes, but it does require you to have access to the source code. For those of you who don't have access to your source code, who are using industrial applications, we have the cluster compatibility mode. This was available on HECToR and should be available on Archer as well. Certainly there's no technical reason, I don't believe, that I understand, but I'm willing to be prevented from that. But this will allow you to run things like ISV applications, which on the supercomputer at almost full performance. There is some possible compromise due to the fact you're having to emulate the performance of a normal Linux cluster. But ultimately, it's a compatibility layer, and this should be available to you. Again, all of these are integrated together. So we're integrating applications with the compiler by feeding back source code, potentially feeding back information from the compiler into application developers. You then go through the static analysis using tools like Reveal, which can automatically add OpenMP loops to directives to your loops. Once you've run your application, you can review the performance using the Cray pattern analysis toolkit, and then again use those to feed back into your application and how it's designed. So it's supposed to be a totally integrated environment using the same tools and the same software suites. So again, primary programming environments that we support, Fortran, C, C++. We do support Python, which is the through the standard distributed executable that comes with the CLE. We have support for a variety of programming models, still continuing that, so primary ones being MPI. But we support SHMEM, including OpenSHMEM, shared memory through OpenMP, and I think we'll be adding OpenMP for support, or intention is through the Cray compiler to add that as soon as possible. For those with accelerator systems, there's the OpenACC models. And obviously a key part of what we provided with Gemini was the support, actually for a long time, the Cray compiler supported the PGAS models, which are gaining, we hope, significant traction with developers as a tool for exascale. Again, similarly, you'll see a lot of the tools and libraries that you would see on the Cray XE6 being ported to the XE30 basically from day one. So if we compare the software stacks between the XE6 and the XE30, we can see that actually the only real changes are at the very, very lowest layer, which are well insulated from the user. So we have the Gemini layer at the bottom two layers, and then that turns to the Aries layer. But a lot of the APIs and programming interfaces that were in common use may carry on over. Again, just to compare this, if we look at a sort of fully Cray system, all of the changes happen at this lowest level, and all of the additional features and complexity that are added to the system remain relatively the same. So there's a lot of continuity between one system, the XE6, and the new system, the XE30. So transition, what is going to change? Inevitably, because it's a brand new system, brand new architecture, we're going to look at new ways of doing things. We're going to try and make improvements. We're going to have to change the way that users work slightly. So compilers. So just like HECToR, there'll be 3 major compilers installed, but rather than having the PGI compiler, that will now be replaced with the Intel compiler. We're only intending to support the most recent versions with the XE30, so the most recent ones in the last few months. We've already had some comments onto whether we can support things from previous versions, but at the moment we intend to start with sort of the most recent versions. Cray compiler, we will coincide with the release of 8.2, which is one of the I'm not sure if it's a minor or major release of the Cray compiler environment. The Intel Composer Suite, which is brand new to HECToR as a whole service. There have been individual user groups that have had access to it, but this should be brand new to users. And the GNU Compiler Collection, GCC, just as you'd normally expect. And these have full integrated support through all of the Cray provided software. So CCE, what's that? If you're looking to move from PGI, what can CCE offer you? Or what does it offer you if you're already a CCE user on the Ivybridge system? It's really one of the few compilers that focuses entirely on HPC. HPC is our major area of research. So we do a lot of vectorization automatically, and we also attempt to do things like shared memory parallelization automatically. We're also very proud of our standards conformance. We tend to implement standards as soon as we can, ultimately. So we're looking at things. We've brought in full support for 2008, one of the few compilers that can do that for Fortran. C++, we're working on things like C++ 11, OpenMP 3.1, again, working on OpenMP 4 as soon as possible, and we'll see as minor releases come, that support will improve. And also OpenACC 1.0, which again, more important for accelerator programming, but possibly something you might be interested in as a user. Well, again, interesting things. OpenMP and automatic multi-threading are fully integrated. So if you do have OpenMP in your application, but it's not terribly extensive, you might be able to increase the amount of threading by turning the automatic multi-threading, and they're effectively using the same mechanism. So you're not losing anything by or having to deal with two different types of threading model. They effectively will do the same thing. Specifically 8.2.0, what is that introduced for XE30 over the versions that you've seen on HECToR? So obviously we've got full support now for the Ivybridge processors, which were recently released with Cray. So it will be optimizing, doing cache blocking depending upon the cache levels, and also all the heuristics are tuned for the Ivybridge processor. We've improved the performance of some of the critical maths intrinsics. That originally said math intrinsics, but I was encouraged by one of my colleagues to anglicize it. Again, we're always investing in new models. So CoArray C++ is a template library that allows you to implement the CoArray style syntax in C++. For those of you interested in Edinburgh, there's a talk, I think it is tomorrow or Friday. I think David Henty is giving that, who in collaboration with the author of the CoArray C++ library, and that's something I think that we're quite pleased with. And also we've recently introduced support, so the GNU and CCE OpenMP runtimes are now compatible. You would have to link with CCE and use program Cray, but at a certain point they should interact nicely. So you could compile code with GCC and CCE and have it work with the threading models. If we look at a comparison between what the feature sets of the CCE, GNU, and Intel compilers, we see a lot of the features that the CCE provides are also potentially available in Intel and GNU. GNU obviously serves a very much larger user base than the Cray compiler, being freely available. It fills many different markets. It has extremely good support for things like C++ and scalar optimization, perhaps whereas Cray compiler focuses maybe on more vector optimization. The defaults are conservative, so always be aware that you should be using things like O3 to improve vectorization and inlining. But again, it's quite configurable, but it's not hugely different to a version that you would download from any sort of standard Linux distribution. Intel compiler, quite aggressive with its optimizations. Default around O2 is giving better performance out of the box than maybe GNU. It's doing vectorization, but it does it in a slightly different way to CCE, so you might need to give it some help when it comes to unrolling or transforming some of the loops. You also might need to, if you have numerically sensitive code, think about how to scale back those optimizations so you can get better floating point reproducibility. But it's a very strong compiler. It's had a lot of investment over the years and has very powerful features. CCE is probably the most aggressive compiler by default. We do, again, knowing our domain, we're going to be using HPC, so we really go for it. Inlining and vectorization, extremely important, especially as we move with the work that's been done for accelerators and coprocessors. Need to do inlining there because you can't call subroutines on an accelerator, so the inlining is extremely powerful. And it also does quite a lot of aggressive floating point optimization, so there are options available to dial that back if you do need things like bit reproducibility. Key feature, OpenMP enabled by default on the Cray compiler. If you have directives in your source code, it will recognize them and enable them, usually the opposite way around on other compilers. Again, this list probably more useful when these slides become available offline, but you can roughly the major things that you might want to do. Get a listing out, find out what actually is happening. Again, Cray compiler we'd feel gives you the best listing information in the most compact form. Intel tends to be slightly more obtuse, comes out in several different files, perhaps more difficult to follow. GNU, again, not fantastic listing information, but the Cray compiler will give you loop mark listings, information about what it did at every single stage. Cray compiler, again, default optimization is usually fine. To get roughly the similar with Intel, you want O2. Add the XAVX instruction for Ivybridge, because that's allowing you to use the AVX registers. That's not actually included as the Cray PE Ivybridge target. Not completely clear on the reasons behind that, but that's an important thing probably to include to get access to those. Similarly, you can see you're having to get quite a lot of extra options with GNU to get to the same level of optimization. Applications that are using non-default reals or non-default integers, sreal64, again, important, but you're probably already aware of that if you're using those or need it. Always look for more information. So big thing that switches, Intel suddenly appears. You'll then be looking at ICC for your C compiler, ICPC for the C++ compiler, and iFort for the Fortran compiler. Again, make sure that you are using the right version of each compiler if you're under any doubt. So you should be able to pass this -v or -- version option depending to the wrapper scripts to let you know what's happening at each stage. For documentation on the Cray, the information is published in the docs.cray, so we provide a book for each major release of the compiler, and the latest one came out this month for 8.2, and again that provides a lot of details about what's going on underneath and what's changed. So how do the processors compare? If we start to look at how Interlagos and Ivybridge compare, the base clock speed is marginally tweaked. We talk about base clock speed even though both have turbo-style features, either upgrade or downgrade. But to be honest, most HPC applications should be saturating the processors to such a degree that they're probably sitting in their base clock frequency most of the time. If we look at cores per die or perhaps NUMA node, then we have 12 with Ivybridge and 6 with Interlagos. But sorry, that's wrong. No, I apologize. That should be 8. That explains something. So we had effectively 32 CPUs for the Interlagos and 24 CPUs or cores for Ivybridge. Major improvement or major change is that we're going to have each core will have one AVX unit, which we can do an add or a multiply on, which is 256 bits wide, which means that you've got 4 operations, so 8 floating point operations per clock, which gives us quite a significantly larger potential flops per node. Again, cache size is significantly increased. So the L3 cache much bigger on Ivybridge. Again, L2 cache is slightly reduced. I think L3 cache is probably where a lot of people are sitting these days. So on a per core basis, you're getting a significant increase in the amount of cache available. Also, the bandwidth between the caches is significantly improved with Ivybridge over the Interlagos. Memory bandwidth to main memory, stream triad, 100 gigabytes per second, almost double. And significantly improve the latency from 110 nanoseconds to 82 nanoseconds. So again, hopefully memory accesses should be significantly improved. Has the stream dropped? Is that okay? Sorry, I got a question about the stream dropping, but let's assume it's working. So how do we construct this? We go back to our original diagram of the compute node. So we have 2 sockets in the compute node. This then gives us these 2 NUMA regions. Each NUMA region has 4 streams to the 32 gigabytes of memory, so giving us 8 streams in total. But you've got to be aware that if you are accessing memory between NUMA nodes, you're passing over this QPI quick path interconnect. Potentially this means that you want to be careful. You don't want your threads possibly straying over the NUMA nodes. Again, this was basically the case with Interlagos as well. You had 4 NUMA regions there. Also, the Aries NIC is attached directly to NUMA node 0. So cores on NUMA node 0 have slightly better performance, slightly lower latency than cores on NUMA node 1. However, we only really see that in practice on synthetic benchmarks where you're testing the absolute raw latency. Once you're in real production mode, the position, that difference is relatively minor. Okay, I've got comments back. Apparently the stream is back. Looking in more detail at an individual socket, there are these 12 cores. There is a very large central cache, which is sort of connected via a ring bus. So data is shuffled around through between the cores through the ring bus. And this is how data is passed up through to the PCI Express bus and the QPI interconnect. Again, not for me. Looking at an individual core, data will, instructions come to the instruction cache, which is 30 kilobytes, are fetched, decoded, scheduled onto one of the three AVX units. Two most important ones for HPC being the multiply and add units, and they're going to be using data initially out of the 32 kilobyte D1, possibly then sharing that up to the 256 kilobyte L2, and again using some portion depending upon how well it's shared or how much contention there is of the 30 megabytes of shared L3. One of the core things, or that's not the right word, but excuse me a second. One of the important features, which I will probably spend a lot more time on than absolutely necessary, is the inclusion of hyperthreads. So hyperthreads are Intel's technology for sharing processor cores between multiple processes without doing a software context switch. And this, the ability to use these effectively can add significant performance gains to your application, but again, the exact details will vary from application to application. I'll go into a little more detail about that later. So placement and scheduling is one of these major features that will change between versions of the between HECToR and Archer. So as always, we will be running a batch scheduler on Archer. So you will be asking for resources from in advance. There's always two phases to this. You ask for the right amount of resource from the batch scheduler, which then assigns it to you. But once you've got that resource, it becomes your responsibility to launch your application in parallel on those nodes using the AP run format. Both of these stages have been affected by the upgrades to the software and hardware, and so will differ from the Cray XE6. So I've started including this particular slide just to sort of clear. Cray has its own terminology, which it uses consistently throughout its documentation, which may differ from other people's interpretations of various terms. So important term is always PE, or processing element. People may think of this as an MPI rank, or maybe a co-array image, UPC thread, or SHMPE. So this is the software process which has its own individual address space. The reason we use PE is because we're not always talking about MPI applications. So PEs might have different threads of execution in them. So threads are logically sort of separate streams of execution that can be assigned to different pieces of hardware, but may share the same address space. So a PE has threads, and a thread will belong to a PE. CPU, this is perhaps the possible most confusing or difficult part. Cray determined this as the minimum piece of hardware that's capable of executing a PE. So it may share some of its hardware resources with another CPU, and in the Intel terminology, this is equivalent to a hyperthread. So each hyperthread is what we refer to as a CPU. We then talk about compute unit, which is the sort of individual unit of hardware or discrete unit of hardware that you would use for processing. And it might be what you would refer to as a core, or what Intel might refer to as a core. So each compute unit may provide multiple CPUs. So because each core provides two hyperthreads on the Intel terminology, each compute unit is providing you two CPUs potentially. And this is important to think of in terms that when we talk about placement. So as I said, these hyperthreads are a feature of the modern Intel processors. I say modern, I can think of at least probably been around for 10 years in various forms. I think they went away and came back again. And it's a way of doing hardware multi-threading, but without doing costly sort of software context switches. So effectively you maintain two process states in hardware, but you only schedule instructions through one pipeline. ultimately, they fundamentally are designed to mask long pauses in execution. So this works very well if you're sitting on, say, a TCP IP network where you've got very long pauses. You can do many, many different things in the time it takes to communicate with Japan from the UK. In HPC, perhaps these long pauses are there for, or are there any long pauses if your application is properly optimized? And if so, is there a good reason for them? Ultimately, it allows the OS to schedule two PEs, two processes, simultaneously on the same core or compute unit, or threads. PEs or come threads. So each thread context is held in the hardware and scheduled automatically and interrupted automatically by the hardware. There's no need for the OS to get involved. So for the Cray XE30, we provide full support for using Hyperthreads, and you can switch it on effectively as a user on a per job, per parallel execution environment basis. So each node views itself as having 48 CPUs. CPUs 0 to 11 and 24 to 35 exist on socket 0 on the first socket, and the second set of CPUs 12 to 23 and 36 to 47 exist on the second socket. And the sharing of resources happens between CPUs which are 24 apart, the 0 and 24, 7 and 31. So that sharing that's basically what you have to be aware of. So what we expect most people to be using is what we loosely term single stream mode. So this, each core has a compute unit. In single stream mode, what we're going to do is we're only going to use one CPU per compute unit, one hyperthread per core. So in total, this means that we're going to have 24 CPUs because we've got two sockets. So without any oversubscription, there can be a maximum of 24 PEs and threads assigned to one particular node. AP Run won't let you schedule any more. So how does this happen? So at runtime, you can choose to switch between single and dual mode using this J notation, J1, J2. So J1 is single stream mode, and so the AP Run binds PEs to ranks, PEs and ranks to the 24 compute nodes in order. So 0 through to 23. So the first 12 are assigned to the first NUMA node in order, the second set to the second NUMA node in order. We're going to completely ignore the existence of ranks 24 to 47 based upon from the user's application perspective. So in all respects and purposes, the J1 option means that you are running on a node which has only 24 CPUs. Again, so if we look at how things are bound by default, we're going to bind them in order. So the first 23 ranks go on the first node, first 24 ranks go on the first node, the second 24 ranks on the second node, and we're going to bind them for the life of the process. So we use CPU binding. This is the default. It means things don't migrate. So one PE is bound to one CPU. If we start thinking about threads, how a thread's created, then what we do is we start using the D notation, the depth notation, to tell it how many cores to reserve for your PE. Sorry, how many CPUs to reserve for your PE. And what will happen is AP Run will go out, launch your application on the right as the master thread on the spaced out CPUs and reserve the other CPUs for use by that PE. And what will happen is as the threads are created, it will bind them in order to the next CPU, modulus by the length of D. So it will wrap them around if you spawn more than you ask for. Each PE is assumed to become the master thread. So it's assumed if you ask for two OpenMP threads, then you will be only launching a total of 2 threads, and the original PE will be the master. If, like the Intel compiler, extra threads are spawned, or you have an application which doesn't maintain the use of threads, then we need to start looking at more complicated binding options like CC none or CC NUMA node, which you can see in the man pages, or we discuss in some of the training material. A lot of this all just applies similarly to how you would use the XE6. So in the J1 mode, effectively it's very similar. You're using just a node which has 24 CPUs. As I said, Intel Hyperthreads, the Intel runtime behaves slightly differently to CCE and GNU. Rather than just spawning the number of threads and keeping them alive, it spawns an additional thread, which is some kind of shepherd thread. And it also has its own binding attributes, which are called KMP affinity, if you look through the man pages, and it will attempt to do its own binding. These interfere significantly with the way our AP run binding works, and our advice is to kind of ignore them. So actually to turn most of the binding off, so to run with CC numinode or CC none, so that the threads aren't bound at all. And this allows the operating system to level the wear across the CPUs effectively. Alternatively, you could study AP run manual page in detail and work out a clever scheme using CC, which is possible, or you can contact either the, I suppose, Archer or HECToR help desks, depending on which system you're running on, or us at the Centre of Excellence for advice. There are ways around this, but they're very verbose. Dual stream placement. This is where we basically enable these extra set of hyperthreads. So effectively you have a second set of CPUs that just form in the background, meaning that you now have a total of 48 CPUs per node. And you do this through the J2 option. So the maximum number of processing elements or PEs and threads that can be assigned becomes 48 without oversubscription. So specifying J2 enables this, and it forces AP Run to start binding things to the hyperthreads. Except it doesn't do it in the same consecutive order. It starts binding things such that the hyperthread pairs are bound first. So it's probably best illustrated. So the first process first PE that's bound will be 0. Second one will go to its compute unit pair, its hyperthread pair, number 24. And similarly, it will just keep doing this all the way through until it gets to 48. Similarly with threads, it will assign them in the same way. So if you have 2 threads, they will most likely be launched on the same hardware, the same compute unit, and they'll be sharing resources. Whether that's the best thing to do will depend upon your application. As I said earlier, I fully believe a lot of papers and research will go into whether this is the best thing to do, and it will probably depend on some research for your application and what it does. So what would we expect? What's some general advice on this? Pure MPI or mixed mode hybrid and NPMD all continue to function just as they did on the Cray XE6. So you don't really have to necessarily worry about it if you're using J1 mode, which is the default. But just remember that the number of Newman nodes drops to 2, so options like -S, which distributed things over your Newman nodes, won't continue to work in exactly the same way. You need to divide by 2 rather than 4. By default, AP Run will use only 1 CPU per compute unit, so that's the J1 option. And we do expect this probably is the optimal way to run most codes. Hyperthreads aren't powerful enough really to sustain full application performance. They're better off being used in other ways, which I'll explain later. Because, as I said, the default mode leaves the hyperthreads open for the operating system to use. So we can make use as Cray using the Linux environment and using our MPI library to make use of the hyperthreads for things like asynchronous progress engines, or what we call CPU specialisation, which is where we take processes that would interrupt your user application and we move them over to the hyperthreads. In reality, probably we'd expect that only the codes which have low computational intensity, which for some reason have either large numbers of pauses or memory access, maybe not memory bound, but things which don't have the intensity of floating point operations that maybe they need to, would benefit from hyperthreads. But at a certain point, it's worth experimenting. Nope, no questions so far. It's worth experimenting with if you're particularly interested or think you have an application which may benefit. PBS Pro 12. Yes, question.
Are you going to go and say anything about placement of threads in mixed mode programming with the hyperthreads enabled? I have a question about that.
So yeah, if we go back to this diagram. So the question was, well, actually, ask the question, yes.
So the question is, if you seems sensible that you bind your process to, in this case, to compute unit 0, and if you specify AP-run-D2 to reserve a space for the thread,
Yeah.
that thread you would want to be bound to compute unit 24 on that slide. But I think if I understand how it works existing, it would bind the thread to compute unit 1, which is maybe not what you want. So do you know how that actually works in practice?
No, I'm afraid I'm lost.
Okay,
So
if I want to have an MPI process that spawns an extra thread using OpenMP, and I want that thread to be bound to the Hyperthread pair CPU, do I need to do anything more clever than just doing AP-run-D2?
So the question was, if you wanted an MPI rank to launch an additional thread, and you wanted that thread to live on the same compute unit, on the same core as the original process, would you have to do anything more sophisticated than use -D? And the answer is no, you wouldn't have. -D would handle it. That's the default way it will work. If you're in J2 mode, so you'd have to enable J2.
Yeah.
If you're using J1 mode, you wouldn't be using the Hyperthread pairs at all.
Okay. The AP-run man page is a little bit confusing.
Okay.
It led me to believe it wasn't doing that, and I hoped it was, because that's clearly the sensible thing to do.
Yeah, okay, we'll look at that, yeah. But that's definitely the way it will assign things. So there is a tool in which I can provide a link to, which we have a little application, which is the source codes on one of the documents called XT High. And what that does is it basically is a very simple application that just says I am rank N of and thread X. I am bound to this process. It is extremely useful to just test your binding with this. It's intuitive. It's not complicated, but it can get really out of hand quite quickly if you're not careful. So it's just easier just to test it with this XTI application. Any further questions? So a question, this is probably going to, so we go back to PBS Pro. So we're continuing to use PBS as we have done on HECToR, but we have incremented the version. This is a requirement to support the, I think, Ivybridge processes, and also to get the ongoing support we need for a software that will last for a long, long time, or length of the service. It also allows us to do several things we couldn't do before. So we should be able to enable a queue which allows quick job turnaround, so some kind of debugging queue, which means that you don't have to sort of sit there and wait while the application queues. So it can become a development environment. However, this upgrade does mean that there's been a change in the way that you request resources. So the MPP notation that you were familiar with HECToR is being deprecated by PBS. So we've taken this opportunity to ban people from using it and to move them on to the supported notation, which is Select. So what happens now is basically, rather than requesting things based on your MPI job, you request numbers of nodes. So you ask for whole numbers nodes, and then once you've got them, you can do whatever you like. So this is what we call the select notation. So what you're asking for are chunks of resources from PBS. And as I said, it replaces the MPP notation, and you should remove that from all of your job scripts if you're just porting over from HECToR. Simplest way to think of a chunk is that it's one entire node of the XE30. So users can submit jobs that request whole nodes or a set number of nodes using PBS Select, and then equals the number of nodes that they need for that job. And that can either be done using the standard hash PBS in your script, or via the queue sub options, as you always might have done in the past. So how do you write your job scripts to be dynamic rather than hard coding? So with Archer, what we've done is we've created a new environment variable called numNodes. And this will contain, at the beginning of your job, the number of nodes that your job's been allocated. So you're then free, once you're inside AP Run, to launch your job in any way that is valid, as long as it doesn't exceed the conditions stated below. So the product of the depth and the number of processes per node must be less than 24 times J. So J being the number of compute units you're going to use. So if you're in J1 mode, single stream mode, you've effectively got 24 CPUs. J2 mode, you've got 48 CPUs. You also can't ask for more nodes than you have allocated to you. So the ceiling or the upper bound, rounding up the number of nodes of the total width of the application, lowercase n, divided by the number of nodes, ppn, capital N, must be less than num nodes. Again, another feature that changes, OpenMP num or OMP num threads is now set to 1. It used to be not set at all. It's now set to 1 by default. Again, it's a feature of it's a consequence of the change in batch scheduler. So if you do have an application that is, even if you think it's MPI, it's always worth explicitly setting this, because some of the libraries, some of the scientific libraries, can start spawning threads automatically for you underneath if this is set to anything other than 1. So it's something to be aware of, that this is changed. So you may say, why I've lost a lot of my selectivity. This isn't as descriptive as I used to have with MPP width, MPPN. So we can add extra options here to pass details to the job. So we can tell it how many PEs we want per node. In PBS's world, they only think in MPI, so they've called this MPI procs. We can also tell it how many OpenMP threads per MPI rank per PE we're going to spawn. These have no effect on the scheduler as far as I'm aware. So you can have these set to almost any value and it won't change. It's only the number of nodes that you ask for that's actually understood. These are just used to pass details into your job.
Unless you give invalid ones.
Unless you give invalid ones.
Then it will reject the job. It won't go. So if you have MPI procs greater than
24.
it just sits in the queue.
Will it?
I did it this morning.
I'll have to check that, yes. Okay, so the question was, what happens if you give invalid ones? My understanding was that it shouldn't make a difference, because we'll check that. We'll make sure that that works or doesn't work. So you should be able to at least be able to give it 48. You should be able to give it 48 MPI procs per node. Anyway, and also we're going to set two other environment variables, num_ppn, which is basically copied from this MPI procs, and num_depth, which is going to be copied again from OMP threads. So you end up, admittedly, you're going to end up with some extra information, but it means that you don't have to do any hacks around qstat to get this information back out. So some simple examples of some batch scripts. He says that, to be fair, he expects to work. So you might calculate the width by multiplying out the number of nodes by the number of processes per node. Go into your, similarly as you always would, go into your working directory so you know you're in the right context. Set the OMP num threads to 1 just to make sure, so you know exactly what's going on, you know exactly what it's set to, and then do the AP run in. Oh, no, that's wrong. Right, I'm going to change that one because that one. There we go. That never happened. So yes, so we can assume these values as expected. The absolute simplest example is this one. We just tell it how many nodes we want, and we use -b for it to pick up the information from the command from the PBS runtime. And what this will do is it will default to MPI procs 24 OMP threads 1. So effectively, it will do all the multiplication out for you. This is probably one of the biggest differences we're going to face between jobs. It's going to be the first thing that all users are going to encounter. So are there any questions? Nope. As I said, there is one group on Archer which have higher memory, which have 128 gigabytes per node instead of 64 gigabytes per node. To guarantee that you're going to get onto those nodes, you're going to have to tell the scheduler that you want nodes like that. So all you have to do is add big mem equals true to the end of your select line, and that will force your job to run on that group. However, I don't believe the scheduler has, if that group, it won't force you onto the 64 gigabyte nodes if you don't specify this. You may run on 128 gigabyte nodes as well if there's space available, because there's no real penalty, but that becomes a scheduling decision as to how much of that you allow. Libraries, so there's some slight improvements and changes to the libraries. There's more libraries available to you. Probably the biggest change is the introduction of the Intel Math Kernel Library. So this is a potential alternative to cray-libsci. Certainly in the early days when we were first porting across to Intel platforms, when libsci was in its early days, MKL was giving very, very good performance and libsci was slightly behind it. These days, I believe they're fairly competitive. But basically, MKL provides a very rich set of scientific and engineering routines. It also provides financial routines as well. So I think if you're looking for Black-Scholes equations, MKL's probably got something in there for you. They're highly, highly optimized for their own processors, so they do put a lot of work into this. It's an extremely effective library, and it can offer you potentially peak, almost as close to peak as you're going to get for the routines it's using. However, it's distributed as part of the Intel Composer Suite, and its distribution mechanism is slightly more complicated, which means we cannot put it inside a module. It mixes up various different MPI environments. It's distributed in binary form only, so it's slightly more complicated for us to link. So if you're using the Intel or GNU compilers, there is a very nice web page called the Intel MKL Link Line Advisor, which will tell you how to add things to your path. So this is one of the few areas where you have to stray outside the FTN wrapper scripts to load modules. You have to add this to your link line. It can be used with the Cray programming environment. Again, Intel don't mention this on this MKL link line advisor, but you can kind of look at it a little bit like the GNU form. It doesn't support the threaded versions of the MKL library because our runtime is different to both Intel, OpenMP. Actually, having said that, the 8.2, this might change. This might be slightly old. The 8.2 with the support for GNU might make this feasible, but let's just assume for the time being the sequential library is the one that you want to use. You have to have the Intel module loaded inside ProgEnv Cray. This technically sounds counterintuitive, but is something that you can do. You could have, but not ProgEnv Intel, just the Intel module. And this will set paths like Intel path for you, so you know where your library is. And then you'd add some pretty extensive junk to your LD library path to get it linked in. Again, as I said, the Intel Link Line Advisor can tell you, you've got to kind of tell it that you're using GNU Fortran, I think. Probably best if you're getting to this level, if you're really doing these tests at this initial stage, to talk to someone from the Center of Excellence or maybe the help desk just to get some advice on how this happens. It's still a little brittle, but it works very well with Intel and GNU. With the Cray compiler, again, because it's not a common compiler they encounter, it's slightly more complicated. MPI library behaves essentially the same way as it did on the XE. So the same UGenie interface. So if you did ever do any kind of DMAP or UGenie application writing, it should work for Aries as it did for Gemini. It's the same MPICH 3 code base. So again, we've moved to MPICH 3. So we now have full MPI 3 support. And again, using the similar vShort eager rendezvous protocols that we described in some of our earlier training. So if you're aware of how the underlying library works, it's very, very similar. There may be some changes to some thresholds, but ultimately the functionality is roughly the same. As I said, we've added extended functionality for the XE. So there's modifications to the MPI asynchronous progress engines which allow us to automatically place them on the unused hyperthreads. So if you don't have the hyperthreads enabled, we can start using them for asynchronously progressing your MPI engine. There is also support for these hardware collectives. So you can do things like barriers and all reduces on hardware, which gives us this very low latency. The bare minimum is you need to add this MPICH use DMAP collective environment variable, but you've also got to statically link, actively link DMAP to your application. And that prevents it running in NPMD mode. So again, it needs a little bit more work and if your code is very heavy in all reducers, then it's something worth investigating. But again, at this stage, it might be worth contacting us at the help at the Center of Excellence or through the help desk to get question. Yes, question.
Do the hardware collectives work on anything other than COM World?
The question was, do the hardware collectives work on anything other than MPI COM World? I'm trying to think. You can define the radix. As the question comes from someone in the room in Edinburgh, my esteemed colleague, Duncan Rowath, who is very intimately involved with the design of these things, is up with the PGAS conference and speaking, I think, tomorrow. He is the person to answer that question. It's not guaranteed, I think. I think it's a try to use the hardware collective engine and fall back to software, rather than must. So the progress engines, if you have asynchronous or non-blocking communication inside your application, I send, I receive, I barrier. Obviously, I barrier doesn't really make sense, but hey, I all reduce, something like that. Then you potentially have the opportunity to overlap your computation and communication. So by default, the Aries doesn't have any more capabilities to do message matching than Gemini did, so it all has to be done on the CPU. But we can make use of these wonderful hyperthreads that we've left idle because they aren't terribly useful for scientific work, but they are very good for doing things, integer work at the same time, like message matching. So we start these helper threads, one per rank, which are very lightweight, and automatically the MPI library will assign these hopefully to the hyperthreads. Again, only internode messages are processed this way, which makes sense. Anything that goes over the Aries, and it's going to be anything using the rendezvous path, because if it uses the eager path, that's automatically just, that doesn't require much in the way of additional processing. Anyway, I've lost my stream of thought there. Excuse me. So what you have to do is export this Nemesis async progress engine equals 1 environment variable, set the maximum thread safety to multiple, so that we're definitely using a multi-threaded MPI library now, and export the use unassigned CPUs to tell it to migrate them to the unassigned hyperthreads. Then just run the application as you normally would. If you're using 2 cores per stream, then effectively you are, if you're using, 2 streams, if you're using dual stream, J2 mode, then effectively you are occupying these hyperthreads with work that could be used for the progress engines. So you've got to sacrifice some of them to use the MPI progress engines. And you do this with a core specialization using this R option 1 to 2. And I'll explain that in more detail. And we've seen that ultimately this can lead to about 10% improvement for applications that can exploit the overlap. So if we look at some of the performance differences, these are some results which I think came out of the Cresta project from my colleague in Finland, Pekka Manninen, and he's shown that even in switching just to MPI non-blocking, you don't lose any performance ultimately. In fact, maybe you gain some, but potentially when the reductions are relatively small, you have the potential to gain 70% of the runtime back. So 70% of your cycles back overlap between computation and communication. Okay, right. CPU specialization. So no matter how well we optimize the OS, no matter how well we remove noise, there still is an OS running. And that effectively means that the user processes will be interrupted and moved from the CPU. So if all the CPUs are in use, then the OS must remove the user process and interrupt it. This normally only introduces a small amount of noise and usually should be averaged out over the entire length of the run, so it isn't much of a problem. However, there are some pathological cases where you have very frequent synchronizations through all reduce or barrier maybe, which mean that you actually see a cumulative effect of these CPU noise issues. CPU specialization reserves some of the CPUs for these OS tasks and also allows us some place to put the MPI progress engines. And it potentially improves overall performance. On the on the XE30, the reserved CPUs are automatically chosen from the hyperthreads, unused hyperthreads, or spare hyperthreads, even if you're using J1. So you can ask for technically more than you have. So you can still ask for 24 CPUs and reserve some additional cores, and they will be used out the hyperthreads. If you use J2 mode, then you cannot exceed 48. So the sum of capital N and R, the sum of the product of N and D plus R cannot exceed 48. So you can't be asking for more CPUs either for core specialization or for user applications than there are on the system. Again, use those environment variables, all available through Man MPI. Oops. So how might you approach this as a sort of optimization process? Start by running your application with no asynchronous progress engines and only in single stream mode, so using one CPU per compute unit. This is your baseline, and it maximizes the available CPU performance. So it means that you've got the maximum single serial performance you're going to get out of the application, but you're sacrificing MPI. Then you might try enabling the asynchronous progress engines to see if you get anything from overlap. Does the overall improve? Yes, no, depends on your result. Alternatively, or both, you might suddenly decide to just run with twice as many ranks or twice as many threads and use J2 mode. So effectively what you're doing is trying to make use for your application of the hyperthreads and see how well those. Again, is that better? Only then do you decide whether you want to try and mix the two. And at that point, you have to start working out how many cores you want to, how many CPUs you want to sacrifice to the asynchronous progress engines and the core specialization. Ultimately, that's the third or fourth stage that you would go through to make sure it works. So that kind of leads us to sort of the end of the discussion of what you might expect from Archer. If you're looking for more help, I believe there's more information on the Archer website. We also will be running an XE30 Advanced Tools Workshop here in Edinburgh in January 2014, 28th through to 29th. We'll be covering in a lot more detail how the fundamental MPI library works, how binding works, and I would recommend it for anyone who's really looking to get the best performance out of their application or wants to understand what the underlying hardware is doing in more detail. I didn't get any questions or any further questions through via email. Are there any questions in the room? If not, I'll leave my email address up on the webcast, and if anyone wants to ask me any questions through that, that would be fine, and I'll stay around for another hour or so, ready to answer any questions. Thank you for coming.